Well, good morning, everyone. We are missing our conveners, but we're just going to get this show on the road. Welcome to the Global Climate Change Session, GC22A, Climate and the Intersects of Water, Energy, and Land Use. I'm your first speaker, so I'll just start with that. Hopefully we'll have time for questions at the end. I want to talk today about our opportunity to integrate climate and water directly into electric sector modeling. As you probably are aware, the power sector is currently experiencing water availability issues, both because of water temperature and water availability. Higher temperatures also impact demand and the efficiency of our energy systems. So what we are doing is integrating climate-affected water availability and cost endogenously within electric sector modeling. And there's also a talk tomorrow in H32A that is related to this. Our main platform is NRAILS READS, or the Regional Energy Deployment System Modeling Tool. It's a capacity expansion modeling tool that's particularly good for looking at renewables because it's highly spatially resolved. If you're going to consider including wind or solar, you need to know what the resource is. So unlike most models, it has 356 resource areas and it's wired together the same way our electric system is. And it projects electric sector growth to 2050 under different techno-economic and policy assumptions. It serves load, meets planning and operating reserve requirements, and obeys physical constraints. So it's a really good way to look at what decisions might be made as you change the constraints. Our water data comes from a wonderful data set that's recently been made available from our colleagues, led by Vince Tidwell at Sandia, that have both cost and availability of different types of water: groundwater, appropriated and unappropriated water, wastewater, and brackish water. Our climate scenarios rely on the CMIP-5 modeling runs. We're looking at hydrology that was generated from downscale CMIP models and selected two ensembles of 5 models each that demonstrated increased, either fairly high increases in temperature and decreases in runoff, which would be a hot-dry example when the data was analyzed for the Southwest, or a more modest set of changes. So we have the moderate hot scenario and the hot dry. Our scenarios are shown here. First, no constraints, basically existing policy from now to 2050. The second is constrained water with no climate change. And then we have 2 constrained configurations, one with a moderate hot climate and one with a hotter and drier climate. The temperature, remember, it affects a number of things. It affects electricity demand, plant efficiency, O&M, the transmission capacity, and total generation capacity, as well as the water withdrawals and consumption associated with each generating type and its cooling type. So let's look at some results. You're probably not used to looking at electricity model scenarios. This is capacity, which is what's built in the system, and this is the generation, 2010, and the 4 scenarios in 2030 and 4 scenarios in 2050. What we see here in terms of capacity is that our temperature rise leads to an increased demand even within a time frame. We also see decreases in ones through cooling for coal and nuclear. Most of the increased energy and capacity needs are met by a combination of wind, solar, and natural gas. When we look at how the system operates, here we see the power output in 2050 for the non-constrained model result. We see 4 different time slices for summer, fall, winter, and spring. And obviously the peak occurs in the summer. The increased demand is primarily met by gas, wind, and PV, but that summer peak requires additional gas combustion turbine, shown here in the black. What's interesting is that the operational water constraints under climate change also reduce generation from once through cooled coal and nuclear capacity. So we see this decrease in generation, which we don't see in the other scenarios. National water withdrawal and consumption are pretty similar across the individual scenarios. Overall, we see withdrawals decreasing because once through cooling is displaced. But even when we start seeing any temperature changes, we see an decrease in withdrawals. While consumption decreases overall, the change occurs later and the magnitude of the effect is smaller. Notice that there are very different axes, units in the axes, so this is a much smaller overall change. Because we're using such a highly spatially resolved tool, we're able to look at some of the regional impacts. Here we see the difference in both water withdrawal and consumption. The two scenarios on the on the left are showing the difference between a water-constrained 2050 and no constraints, and on the right we add on the climate impacts. Overall, we see a decrease in withdrawals and a slight increase in consumption when we start putting in water constraints, but these effects become much more accentuated when we add in the climate impacts, which are largely temperature-driven. We see tremendously big impacts in decreased withdrawals and a great deal more consumption, primarily in the entire eastern U.S. over time. Moreover, the water that is being tapped is basically more expensive water. Here we can see the cost, or the cumulative water access purchase, over time in the different scenarios. And the blue is the unappropriated surface water. And we start seeing that constrained. We see a higher reliance on surface water from retirements of other generators and the increased use of more expensive water that needs to be treated from alternate sources. And that's really important because water might be available for 3 seasons, but a power generator needs to ensure that it's also available during that 4th season when the demand increases. And that's what's really driving some of these decisions. We can also look at what happens in terms of what kind of technologies are being built out over time. These 4 show the deployment of solar, wind, natural gas, and coal over time. In 2050, when we just impose some water constraints. There are some changes in the southeast for solar. We see wind, some changes throughout the U.S., and same thing with natural gas, and a few isolated areas where coal is being affected. More importantly, when we start adding in the temperature-driven climate impacts, these changes really solidify and accentuate. We have a lot more solar being built in the southeast. Wind and natural gas are being now built throughout the U.S., and a great deal less coal is being built out or relied upon in the west and in the south. So to summarize, we've created an integrated platform that enables us to evaluate the impacts of climate change on the operations and the future developments of the U.S. electricity system. We have some initial results, and they show some regional trends, but more importantly, they're beginning to highlight the, national trends, but they're also highlighting the regional differences. And this framework is now available for evaluating the implications of different policies or other factors. And I think I will stop there. Any questions? Do we have time to get on schedule?
Until it goes black, I guess.
Well, no, I wanted to get back on schedule, though.
Oh, okay.
Yeah. There's a question? Yes.
I was interested to see the dominance of wind, solar, and gas in your baseline and future capacity. What fossil fuel prices and climate regulation scenarios underpin that baseline?
I didn't skip to this one. This shows the assumptions and the sources for all of our cost data. One of the things that for example, for nuclear, we're only looking at a 60-year retirement time frame for nuclear, and as you know, they're actually considering extending that. No new nuclear is built because the cost for that is too high as those nuclear plants are being retired. Of course, that could be modified. Fossil are based on current projections, and I think here you can see the source. It's basically using the AEO 2014 reference scenario. Any other questions? I'd like to get us back on schedule. So our next speaker is Jenny Rice, and her talk is Climate Change and Future U.S. Electricity Infrastructure, the Nexus Between Water Availability, Land Suitability, and Low Carbon Technologies.